I'm going to pull the chat up in case there are lots of questions this morning before we got started for lectures. So I will definitely answer any of those. I don't see any right now, but I sent an email yesterday. So hopefully you read that email just with some updates and reminders and due dates for the week. You guys all finished up your chapter 1 homework last night. And chapter 2 homework is now available. You can access it, and it's due next Monday night. But since it's Labor Day, nobody wants to do homework on Labor Day. I just encourage you, don't wait around last minute for that. Secondly, all the dry lab work, remember, is due this coming Friday, September 4th at midnight. And so make sure you have that done. I posted videos. Have you guys checked out the videos, seen the videos that I posted? I'm getting some head nods. Okay, good. Use those. And then I also yesterday, and I think the last one got uploaded this morning, the complex conversion problems from the end of lecture this past Thursday. The ones we did not get to work at the end of lecture. I made videos step by step of how I would go about solving them, and I uploaded those. So please take time to work through those on your own and then refer to my videos as you need them. I would not encourage you to just jump on and see how I do it. I want you to attempt it yourself first, because on the exam, it's just going to be you. And so remember that. We have a quiz on Thursday as well. It'll be the same format as we had for quiz 1. So anything else I'm forgetting, let me know if you think of it or have a question. But other than that, we will get going with our lecture for today. We're going to start chapter 2. Oh, also, I told the people this morning, in your textbook, at the end of every chapter, there is some pages that just have lists and lists of problems. And before, like if you're someone who wants some extra practice problems to work or to rework, I definitely encourage working some problems from the back of the textbook, back of each chapter. But I'm going to come up with a list of those and give you the ones I recommend, because there's sometimes I wouldn't recommend every single problem from the back of the chapter. That would be a lot, number one. And then 2, there's certain problems that just don't apply. There's certain things we didn't get into very much from the chapter. So I'll send a list out of problems I recommend that the closer we get to exam 1. And then I will even make a few videos of how to work certain problems that are textbook problems. So you can use those as resources as well to study and get ready for exams and things like that. So, all right. Well, I'm going to share my screen and we will get started. Okay. So chapter 2, this is a new lecture. So we're going to start out with a new hiking picture. And I'm kind of stuck in our Grand Canyon trip for a little bit just because I got a few good pictures of different hikes we did. This is a different trail we did, obviously, at the Grand Canyon. Day 1 of lecture, I showed you guys a picture of a trail we hiked at the Grand Canyon out to Plateau Point. If you remember, the trail was called Bright Angel Trail. And this is called the South Kaibab Trail. They're all on the South Rim. We only hiked trails on the South Rim. And so this was maybe the most taxing hike we did, and because we went all the way to the bottom. And so it took us all day. So we got started at, like, you can tell this is pretty early morning when I took this picture. We were just getting started on the trail. You can see the switchbacks kind of as you go down the mountain. And then here's the river down in through here. And so we hiked all the way down into that crevice I just outlined, down to the river. There's actually a ranch down there called Phantom Ranch. You can go stay in cabins, but you have to like book it a year in advance or more because it's not very big. But anyways, yeah, this was an amazing hike. And so totally recommend it. I can't hear you. I'm going to leave and come back. Okay. Yeah, if you ever run into technical issues, can't see me, can't hear me, hop off the Zoom and hop back on. No problems there. All right. So anyways, anybody ever been to the Grand Canyon? Type it in the chat. I would love to know. But if you haven't been, it should totally be a bucket list item for you. Me and my husband are not professional hikers. You don't have to be. Now, if you have like a massive knee or foot injury, I don't recommend, you hiking all the way down. But it is a phenomenal trip for sure. Okay. I put this slide in this time to give us a summary of what we're going to get into today. This is again out of chapter 2. I hope that you're keeping up with the chapter readings. So there were a couple sections like 2.1, 2, and 3 from the textbook that you should read or should have read for this lecture. Please take those seriously. Please do them. But today we're going to get into Dalton's atomic theory. So there's 4 parts to that. We'll go over those and then we'll do some review. I actually wrote some polls like we did day 1 of lecture that we'll make sure we're understanding things clearly, and then we'll get into the structure of atoms, protons, electrons, neutrons. Maybe some of this sounds like some review if you've had a chemistry class before, but we're going to get into those things. And then lastly, we're going to talk about isotopes and why those are important, even from a healthcare standpoint, how we use them in medicine, things like that. And then we'll save these last 2 topics for Thursday, okay? So we'll get in the periodic table and valence electrons on Thursday. So let's get started. Dalton's atomic theory. So back in the day, I don't know how long ago, a long time ago, well before we had things like microscopes and just modern technology, there were philosophers, Greek philosophers, there were scientists, and they kind of hypothesized that matter, because we talked about what matter is stuff, anything with a mass or a volume. Matter is made up of small particles that were so small that we couldn't even see them. And they were right. And we've since found out, and we've called those particles atoms. Now, what they didn't know is that atoms are even composed of smaller particles, and we're going to talk about those today. But essentially the first part of Dalton's atomic theory, if we summarize kind of these 4 fundamental truths about what matter is made up of, the first one is that all matter is made of tiny particles called atoms. Okay, you likely have heard of an atom before. If not, then they're incredibly small. We cannot see them. We have to have microscopes to see them. The Greek word atomos is the word for invisible. It's where we get the word atom from. But essentially, what we're doing today, to kind of give you an analogy, we're going to play a quick game. And we're zooming in to matter. We're looking at it at a microscopic scale. Okay, we talked about different properties, and these are kind of macro level properties. We can touch them, we can see them in lab this week or last week. You did an experiment where you're holding test tubes and you're looking at different properties. Pause again. I think maybe a couple of you are having issues hearing me. If you can't hear me right now, know that this lecture is recorded and it will be recorded. So just communicate with me and I will make sure the recording's posted and I will know that you were present for the lecture. Okay. Let me respond to this comment, guys. Hold on. All right. Let's continue. So looking at these pictures, I don't know if you've ever played a game that's kind of like the zoom in game or the close-up game. I don't know what maybe you've heard it is called. I have 4 pictures here, and I think you should have them on your slides as well. And I want to know what you think these are. So take a second in your notes, write down what you think. I'm going to zoom in on number 1, because this is what we're doing today, concept level wise with our lecture. We're zooming in and we're talking about matter at a small scale. So what is picture number 1? What do you think? Write it down on your paper. Once you get number 1, write out what you think number 2 is. And I'll give you a hint. These are some pretty common, ordinary things. These are not like super fancy organism sciencey things. Once you get number 2, give me your best guess for number 3. It's not a wad of bubble gum, I can tell you that. And number 4 threw me. Number 4 definitely caught me by surprise. So write down what you think they are. Go ahead and shoot an answer in the chat if you think. Let's look at what the answers are now. What do y'all think number 1 is? Spaghetti. Somebody said relish. Okay, well, number 1 is spaghetti. We'll see in just a second. So if you think it's spaghetti, yeah, they're noodles. Okay, what do y'all think number 2 is? an orange, a flower, the sun, a mango. All right. What do y'all think number 3 is? A jellyfish. It's a good guess. All good guesses. Somebody said a sponge. Y'all all think a sponge. Are y'all cheaters? Y'all are all cheaters. What do y'all think number 4 is? Nobody's going to get number 4. Oh, come on. How do you know it's chocolate? There we go. So number 1 was spaghetti noodles. Number 2, these are carrot slices. Who knew? I think this photo has been tampered with. Okay. And then y'all were right, a sponge. And what do you know? Who knew? Chocolate looks like that close up. They're cheating us. This is not premium chocolate. Premium chocolate doesn't have that much air in it, right? Okay. So that's what we're doing today. We're looking at matter close up. We're getting down into the microscopic level of things. So that was point number 1. All matter is made up of tiny, tiny particles. We're actually going to look at the structure of those and see how they're arranged and what they look like close up. Number 2 is that atoms from the atoms of all other elements. Okay, so each element is characterized by the mass of its atom, how much it weighs. And we're going to talk about what portions of the atom contribute to its mass. But essentially what you need to know is atoms of the same elements have the same mass. Okay, that makes sense. Atoms of different elements have different masses. So we're given an example here. Na, who knows what Na is?
Salt.
Sodium.
It's sodium. Yeah, it's a portion of salt. Okay, so we have sodium, and then N is nitrogen. Did I get anybody on the quiz? If y'all remember on the quiz, you had to write the phenylalanine. You had to pick which was the correct chemical formula for phenylalanine, and one of them I had like C9H11NiO2. Okay, Ni is not nitrogen. Ni is nickel. Okay. So N is just nitrogen. And if we look at the masses of these, we see that sodium is almost 23. And y'all are probably wondering, what are the units? Your mic is lagging for me sometimes. Okay, here's what I'll say. Probably because the weather, things may not be crystal clear for you. And if it's to the point where it's giving you a headache just listening to me, I'm just not gonna really I will keep track of attendance today, but if you have to check out, then I will know. I'm not going to count you absent if the mic and everything is messing up. I thought I was the only one. Same. Is it terrible? Is it to the point where y'all just like can't even understand me? How bad is it?
It's just every once in a while. It's not that bad.
Not that bad? Okay. Well, here's the deal. I'm going to keep going. Okay, I'm going to keep going. If you just cannot understand anything I'm saying, you're welcome to hang in here and take notes because you know we do a lot of fill in the blank. But I will record this and I'll post this, and we'll be pretty flexible with attendance today. Okay, just keep that in mind. All right. Okay, so back to the masses of these things. So the units on this, and we're actually going to get into the units for elements. It's a unit called an AMU. So I'll explain what this acronym is in just a second. But you can see for sodium, it weighs almost 23 AMUs. It's almost double, well, not double, but it's definitely bigger than a nitrogen atom, okay? So different elements weigh different things. That's essentially what the second part of Dalton's atomic theory says, all right? Their masses are different. Okay, part number 3 says that compounds consist of atoms in specific ratios, and only whole atoms can combine into compounds. Okay, so we're going to actually do a poll question on this to make sure you understand what I'm saying. We form unique substances, unique compounds, when elements join together in different ratios. So you can have the same elements put together, but if they're put together in different ratios, you get different compounds. For example, water is H2O, Hydrogen peroxide also has hydrogen and oxygen, but it's a different ratio. This one, 2 hydrogens for every 1 oxygen. It's a 2-to-1 ratio. Hydrogen peroxide is H2O2. 2 hydrogens for every 2 oxygens. So it's a 1-to-1 ratio there. So you see that when we get different specific ratios, you can have the same elements, but you get unique compounds, okay? Now, the point to say with number 3 is that you cannot cut an atom in half and join half an atom and make a compound that way, okay? They join together in whole atoms are what join together. So if we're looking at these A, B, C, and D down here, I'm going to launch the first poll question. Launch poll. Okay. Hopefully you see the screen, the poll screen. A, B, C, and D correspond to the one on my lecture slide here at the bottom. So make sure you can see that for your choices. I couldn't use subscripts for numbers when I typed in the formulas, so I didn't want to mess you guys up by not typing the numbers as subscripts. So which one of A, B, C, and D here on my screen is incorrect based on part 2? Or actually, it should be say part, that's a typo, part 3 of Dalton's atomic theory. Which one's incorrect? Almost everybody, we're getting there. Got about 15 people left. A few more seconds. Go ahead and get your answers in. Which one is incorrect? Which one does not have specific whole number ratios? Almost there. 3 or 4 people left. All right, I'm going to call it in the poll. Okay, here's the answer. So most of you got that right. So D is incorrect. Why? If we zoom in, we see that we have, this is not a whole number. You can't have a fraction. This is 3 halves is 1.5 oxygen atoms. We can't have that. Okay, so it's got to be whole numbers. You can never have fractions or decimals. You have to join atoms together in specific whole number ratios. Okay, part number 4. This is the last part of Dalton's atomic theory. I'm going to close the poll. Chemical reactions only change the way atoms are combined or arranged. They do not change the type of atom. Okay, so we can't take, we can't take an atom of iron and just turn it into an atom of silver. All right, you can't. They only rearrange them. They break bonds and they form up with other atoms, but they don't change what kind of atom they are. All right, at least in chemical reactions. Okay, if we were talking about like nuclear fusion or nuclear fission, those are different processes. But in a chemical reaction, bonds break and atoms rearrange. You don't change the type of atom. So what we're saying here is that atoms are recycled all throughout planet Earth. The same carbon atoms that maybe formed trees or formed, different organisms thousands of years ago, maybe are a part of, the food we're eating today. And to give you it's actually a really dumb illustration, but I don't think you'll forget it. It's kind of gross. The same atoms that are in the roadkill that we pass every day are the same atoms that could end up in our Subway sandwich. Okay, it's true. Actually, it's very true. And if you look closely, all sandwiches, they should say made from 100% recycled atoms, right? Now, this is a dumb example. If you've actually heard, the human body is constantly replenishing its cells, right? Not just when you get a wound and you heal. Not just when you get a wound and you heal do you regenerate new cells. Your body's constantly regenerating new cells, and I think it's every like 7 years or so that they say your human body is composed of a new set of cells, roughly. So anyways, all that to say, atoms are recycled. We have a set number of atoms. We don't create new atoms. We don't destroy atoms. We just rearrange them. Okay. All right. So that's Dalton's atomic theory. I'm going to do a little review real quick. So we're going to have another poll question. So let's look at this poll question here. It says, which statements, so there could be more than one, are consistent with Dalton's atomic theory? Which ones fit? Okay, so again, I don't know. I'm kind of new with Zoom polls. I don't know if you can select more than one answer. but I believe there's more than one that's correct here. So you can read them. Sulfur and oxygen atoms have the same mass. Is that consistent? All cobalt atoms are identical. Is that consistent? Potassium and chlorine atoms combine in a 1-to-1 ratio to form potassium chloride. You're looking at the numbers on the ratio there. Lead atoms can be converted into gold. So which ones do you think are consistent?
It only let me select one.
Only let you, can anybody select more than one? Ah, man. Well, and I tried to see, you can either do it says a single choice or a multiple choice question. And single choice didn't sound right. So I went with multiple choice, but we'll talk about which ones. So for sure, select one. If you're on your phone, you can. Okay. Good to know. We'll go over which ones are correct. So just select one that you know is correct. There's two, I believe, that are correct. Almost done, 87%. Go ahead and get your answers in. All right, I'm gonna call it end poll. So B and C, these are consistent. Sulfur and oxygen, they're two different elements. And part 2 said that different atoms of different elements, they have different masses, okay? So A is not consistent, B is consistent. Cobalt atoms are all identical. They're all gonna have the same mass. C, potassium and chlorine atoms, a 1-to-1 ratio, so this could be possible. Those are whole numbers. So C is consistent, and then we know we can't destroy an atom and turn it into another atom. So you can't take lead atoms, I wish, right? And convert them into gold. Okay, we're gonna do one more. So again here, I believe there's probably more than one correct answer, but just pick the one that seems correct. Now we're looking at which statement is inconsistent with Dalton's atomic theory. Man, the rain. Do y'all hear the rain? Okay, all carbon atoms are identical. Is that inconsistent? An oxygen atom combines, there's a typo there, but combines with 1.5 hydrogen atoms to form a water molecule. Is that inconsistent? 2 oxygen atoms combine with a carbon atom to form a carbon dioxide molecule. Is that inconsistent? The formation of a compound often involves the destruction of one or more atoms. Is that inconsistent? While we're waiting, there's about 10 more people. We had my daughter's 2nd birthday this Saturday, and she got a cupcake, and it was a big cupcake. So I was like, I can't let her eat all this because, well, I just can't. It's too much sugar, right? And so about halfway through, I was like, okay, Finn, her name is Finley. I was like, okay, Finn, we're gonna take the cupcake now, and I'm gonna save it for you and you finish it later. And let me tell you guys, if I learned anything over the weekend, you don't take a cupcake away from a 2-year-old very easily. She cried at her birthday party. I made her cry. It was terrible, but I did take it. Okay, I think we're about done. I'm gonna call it end poll. Okay, so which one's inconsistent? Definitely B. You cannot have 1.5 hydrogen atoms, but there's another one that is inconsistent. Okay, D, the formation of a compound often involves the destruction of one or more atoms. We don't destroy or create new atoms, we just rearrange them. Okay, so D is also inconsistent as well in this poll. So these are the style of questions, because let's face it, Dalton's atomic theory is a conceptual thing. There's no math involved here. There's no problems we're going to work. So these are the style of questions I would want you to be familiar with on the exam. If you're thinking, how do I study Dalton's atomic theory? Well, you just need to know the 4 parts, and you need to think, how do they apply to things like elements and compounds, stuff like that. So, all right, get rid of this poll. So now that's the end of Dalton's atomic theory. We're going to get into the structure of atoms. We're going to talk about protons. electrons, and neutrons. Okay. So looking at this slide, we're going to look at the structure of an atom. So essentially an atom has two parts. The first part we call the electron cloud. The second part is the nucleus. Okay, and you can see the nucleus is this small central part, and we can zoom in on it and see that there's a lot going on in the nucleus. There's multiple kinds of particles and things like that. But the bigger part, the portion that makes up the size of the atom, is the electron cloud. Okay. So now, how big is an atom roughly? We said they're invisible to the naked eye. Well, if we zoom in here, approximately, atoms can be all different kinds of sizes, but they're on the range of, look here, 10 to the minus 10 meters. If we were to put this in prefix notation, if we were to pick a prefix, which prefix is most appropriate for this? What do y'all think? What prefix would be most appropriate? 10 to the minus 10. Now, this is not one you had to memorize, but anybody happen to remember which prefix that most closely fits? Huh?
Micro?
Even smaller than micro. Nano. Okay, thank you, Zoe. So 1 nanometer is 10 to the minus 9 meters, okay? So essentially there's 10 to the 9 nanometers. You can write it this way as well, in 1 meter. So atoms are down on the range of nanometers is what I'm trying to say. Now again, different atoms are different sizes, and we'll get into that later. But electrons are here in the cloud. Another thing, you're zoomed in, we can see what you're writing. Can y'all see what I'm writing?
No, it's zoomed in too far.
I zoomed out. It must be frozen. Let me reshare. What about now? Better? Okay. Frozen. It was frozen. Frozen is invading every area of my life. That's like the only movie we watch at my house right now. Okay, so electrons are in the electron cloud, and here's what you need to know about electrons. We're going to fill in this table at the bottom in just a second, but two things about electrons. I'm going to zoom back in for just a second. Electrons, number one, they are always moving. Okay, they have a lot of energy. So they're always zooming about the electron cloud. Now, here's a question. Why don't they just fly off into oblivion? What keeps them orbiting the nucleus? Well, we're going to get to that in a second. Two, they are attracted to protons. Okay, and that's what keeps them from flying off into oblivion. That's what keeps them orbiting the nucleus. Now, we're going to look at how that is. Now, we look over here at our picture of the nucleus, you can see there's a couple things. Number one, we have protons. Okay, those are the red spheres. Two, we have neutrons. Those are the blue spheres. Protons have a positive charge. Neutrons do not have a charge, no charge. Okay, and we'll talk about electrons in a second. You can see the nucleus is even smaller, 10 to the minus 15 meters. There are prefixes that we didn't even get into at this class that go down to that level, but you don't have to know them for this class. Let's fill in this table. So we have these three we call these subatomic particles. If I say the word subatomic particles, I'm talking about protons, neutrons, or electrons. So how do we abbreviate these? What are their symbols? We just use the letter. They start with P, N, lowercase n, or E, okay? And with the electron, though, we put a negative sign by it. All right, so those are the symbols. What about their masses? Let's look at this for a second. In grams, look at these numbers. 1.673 times 10 to the minus 24. That's ridiculous, right? Like that's an absurdly small number. And then you can see neutrons are about the same. They only differ in their third decimal place. So neutrons and protons, what you need to realize is they weigh about the same. Electrons, if we look at these, look at the exponent here. The exponent is on a magnitude of order of 4 smaller, okay? So protons and neutrons are 10 to the minus 24. Electrons are 10 to the minus 28. So essentially compared to a proton and a neutron, electrons weigh, their mass is 1,000 times smaller. Now, because these numbers are just ridiculous, they're really, really small, we came up with a new unit to make this more manageable for us to think about. So we came up with what we call the AMU, and I wrote this earlier. AMU stands for Atomic Mass Unit. AMU. And thankfully, scientists decided to make this real easy. They said in AMUs, we can define the size of an AMU because we created it. A proton is going to weigh one AMU. That's a lot easier of a number to deal with, right? And because neutrons and protons weigh the same in grams, they weigh the same in AMUs. So about 1 AMU. And because electrons are so much smaller than protons and neutrons, we say they don't weigh anything. So there's 0 AMUs. All right, lastly, let's look at the charge. So 2 of the 3 of these are charged. Protons, we said, have a positive charge. Neutrons, no charge. And electrons have a negative charge. Okay? Now, the biggest thing to know with the charges is obviously because protons and electrons have the opposite kind of charge. What do you know about opposites? Opposites attract. That's why electrons and protons are attracted to each other. So if we zoom in on our picture here and we made this a positive charge and we see the electron has a negative charge, there is attraction here, all right? So why doesn't an electron just get sucked into the nucleus? Well, because remember, they're always moving. They have a high amount of energy. So they're constantly moving about and they're pulled towards the nucleus at all times because they're attracted to the positive charge. So that's what gives atoms their shape, all right, or a definite size. Okay, questions on this slide? Let me pull the chat up because I can't see it anymore. All right, let's keep going. So beyond knowing, you need to know how protons, neutrons, and electrons are arranged in an atom, and then you need to know their charges and their mass in AMUs. You also need to know what role do they play in the atom. Why are they important? So electrons, they're responsible for the chemistry. Okay, if an element is particularly reactive or explosive, for example, down here we have a picture of a big explosion. What is this a picture of? Can anybody guess?
Atom bomb?
That's a hydrogen bomb. Okay. Now I don't know how far away this picture was taken, but you can tell it's a big explosion. This is because of electrons. Isn't that crazy that something so small can cause an effect so big? Okay, so this is responsible for the chemistry. And they also balance protons. What I mean by that is if you have an atom that has 10 protons in its natural state, it should have 10 electrons. Okay, you have the same number of protons as you do electrons. If you have 20 protons, you have 20 electrons. If you have 150 protons, you have 150 electrons. Okay, and we say that atom has a neutral charge overall. Why? If you have 10 positive charges and then you have 10 negative charges, these cancel each other out. And overall, the atom is neutral. Okay, that doesn't mean anything went away. It's balanced. All right, protons. What's the role of a proton? Well, they identify an atom. Okay, they're the ID. We look at the number of protons to figure out, okay, is this an atom of carbon or is this an atom of hydrogen? All right, if it has 1 proton, it's hydrogen. You can look at the periodic table. If it has 6 protons, it's carbon, so on and so forth. So they identify the atom. They contribute to the mass of an atom. So whatever an atom weighs, the protons contribute to that. And then they balance the electrons. Lastly, neutrons. What are they good for? They contribute to the mass as well. We know they weigh 1 AMU. And they are what we call the nuclear glue. What do I mean by that? Well, remember, protons are positively charged, okay? In fact, I want us to look up here at this picture of the nucleus again. If we have a bunch of positive charges all crammed together, what do you know about positive charges? If opposites attract positives, they repel one another. So how in the world do all these protons stay stuck together in the nucleus? Well, there's things at play beyond the scope of this course, but the neutrons are there to buffer the positive charge, and that's why we say they act like the nuclear glue. They help hold the protons in the nucleus, okay? Okay, so know the roles of these subatomic particles, know their charges, their mass in AMUs, and you might look here, yes, there are decimals, and these will actually be important when we talk about isotopes, because when we come up with the exact mass of any element, we do take into account that there's decimals here. But I don't want you to memorize these numbers. You just need to know their mass in AMU as a nice round number, 1, 1, and 0 if you're an electron. Okay. Also, I put this link in here. This is a fun video. It's just really quick. There's an old TV show back in like the 70s or 80s that one of the instructors on the TV show actually explains an atom using street gangs. It's just a fun analogy that I think will help you remember it if you like analogies or want it explained another way. So there's that. We're not going to watch it today. Usually if we were in person, I would show it to you, but we are going to do a poll to see how well do we understand what we just talked about. Okay, here's our last poll for the day. Which statements about subatomic particles are true? If an atom has an equal number of protons and electrons, it will be charge neutral. Electrons are attracted to protons. Electrons are much lighter than neutrons. Protons have twice the mass of neutrons. And again, I think there's more than one correct answer here, but just if you can only pick one, just pick one of the correct answers. We'll go over them. All right, I'm going to call time. That's pretty much everybody in the poll. Okay, which ones are true? Definitely A is true. If an atom has an equal number of protons and electrons, it's charge neutral. Okay, the positive and negative charge is balanced, so we say overall it doesn't have a charge. So A is true. B, electrons are attracted to protons. Absolutely true. Electrons are negative, protons are positive, opposites attract. C, electrons are much lighter than neutrons. Yes, that's true as well. Okay, and then on the order of 1,000 if we're talking about grams. And then protons have twice the mass of neutrons. That is not true. So looks like you guys have a pretty good understanding of that. That's it for structure of atoms. If you have questions on that, let me know, but we're gonna move on to isotopes. And that is our last topic of the day. Now, first, before we get into this, what is an isotope, blah, blah, blah. Why should we care about isotopes? What are they used for? Why are they important? Well, the first thing that they're used for is energy, okay? So you guys, if anybody lives in like Northwest Arkansas, then you probably drive past Russellville all the time and you see the big nuclear reactor that's off to the side of the interstate, the big kind of looks like a smokestack. It's a nuclear reactor, and here's what's happening. Nuclear fusion of hydrogen isotopes produces large quantities of energy. Now, I don't know what all they're doing there in Russellville, but here's a picture of 2 hydrogen isotopes, right here and right here. And when they collide together, when you fuse them together, they give off tons of energy. In fact, look at these numbers. Now, you don't have to know what this unit is. I will tell you an EV is an electron volt, but I do want you to guess, what does that capital M stand for? That's a prefix. Now, this is not one you had to memorize, but it is one we mentioned. Somebody said it.
Mega.
Mega. Okay. This is bigger than a kilo. Okay. So a mega electron volt. So you can see it creates 3.5 mega electron volts there, 14.1 mega electron. So fusing two hydrogen ions, just two, produces tons and tons of energy. Now, back in the 50s and 60s, when nuclear energy was kind of up and coming, there were some, it's very dangerous as well, by the way. Even though the plus side is it produces a ton of energy, the downside is it's dangerous, right? A nuclear explosion is a lot more painful and a lot worse than other forms of energy, burning coal and things like that. So that's why people got really skeptical, because we had some nuclear reactors explode in different places around the world. So they kind of backed off from using that kind of energy. But 2020, we're actually back into using nuclear fuel, okay? So a lot of our cities, a lot of things run off of nuclear energy. All right, so there's that. Another reason we care about it, and again, this is because of isotopes, is from the standpoint of medicine, these are useful a lot of ways. I'm going to give you one example. There's more reasons than this, but I'm going to give you one example. Some isotopes we have discovered are what we call unstable, meaning they decompose randomly, rapidly. They're not stable. Now, obviously, we don't want those kinds of cells in our body, but there are times and places we can use those kinds of atoms to do good things in our body when we have bad things in our body. So, for example, decomposition of unstable isotopes releases radioactive energy. And you guys know this is used in all kinds of cancer treatment, but that is what we use to kill cancer cells. So here's an example. Thyroid cancer. Maybe you know somebody with thyroid cancer. I know several people that have had battles with thyroid cancer. They use iodine, okay, iodine therapy. They use iodine, and the isotope is 131. Okay, this is not the natural kind of isotope or iodine. It is an isotope of iodine. Now, I know you don't even know what an isotope is yet, but here's what they do. They drink it, radioactive isotopic iodine. They drink it. It is absorbed through our digestive system, gets into your bloodstream. The thyroid, okay, if we're trying to kill cancer cells in the thyroid is what absorbs most of our iodine. And the radiation there is given off, and that's what destroys the cancer cells. Now, you'll notice it says absorbs most of the radioactive iodine. And it's true that probably not 100% of that iodine goes all the way to the thyroid. And so it could be damaging on other parts of the body. Additionally, radiation is not contained in a patient that drinks radioactive iodine. Radiation is emitted outside of your body. So we have to be very careful. That's why I put this as health professionals. It's critical that these patients are quarantined if they need to be until they're no longer radioactive. Because you don't want radiation, you don't want to be walking by a pregnant lady, you don't want to be walking around kiddos and emitting radiation, right? So you have to be careful when you get these kinds of treatments, how you go about them. But anyways, that's one way we use isotopes. That's two ways we use isotopes. So they're important. I want you guys to care about them. Now, really quick, before I define what an actual isotope is, we're going to look at two properties that are going to help us understand isotopes. The first property of an atom is called the atomic number. And this is just the number of protons. So we abbreviate it with a Z. I didn't come up with this, I promise. But we abbreviate it with a Z. And this is the number of, or I think right here, Z is the atomic number. And this is the number of protons in an atom, okay? This is the identity. We said that. It's the identity of an atom, okay? The number of protons identifies that particular atom. So for example, carbon always has 6 protons. And if you're looking at a periodic table, here's like an example, the square, the number on top, and sometimes it might be over here in the corner, but that is the atomic number. The number down below, that's the mass of that element, okay, or an atom of that element. All right, so that's the atomic number. The other property I want to talk to you about is the mass number, okay? I don't know why, but we abbreviated A. and A, so A is the mass number. This is the sum of protons and neutrons in an atom, because those are the things that make up the mass of an atom, right? Protons and neutrons. So collectively, we have to account for all those in the nucleus to get the mass of the atom. And then we mentioned protons require neutrons to buffer the positive charge and stay in the nucleus, okay? So what is an isotope? I actually want to find a space to define this really quick for you guys. Let me see. I'm going to define it right here, and then we're going to scroll back up. Isotopes are atoms with varying numbers of neutrons, okay? An isotope is an atom with a varying number of neutrons. So what that means is you can have two atoms that have the same atomic number, and then they can have different mass numbers, okay? Their Z property can be the same, and their A property, their mass number, can be different. And that is exactly what we are getting at here with our example with copper. So copper can be stable with 34 or 36 neutrons. So these are two isotopes of copper. So what is Z for copper and what is A for these two forms of copper? Z will always be the same. Why? Because that's the identity of the atom. And here we're talking about copper. So Z cannot change. That's the number of protons. So I put this periodic table here, but it's actually kind of blurry when you zoom in. Copper's right here. And if you look closely, it's 29 is the number of protons. So Z equals 29. There's 29 protons. But what would A be? So if I have 34 neutrons, 29 electrons, what is A for this first isotope? Can anybody get that for us?
Like 70 then, right? If you
Like
add all
70,
together.
close to 70. Anybody know exactly what it is?
It's 63.54.
Well, these are whole numbers that we're dealing with, 29 and 34, so 63. Yep. Okay, and so if we have 36 neutrons, there's going to be two more. So A for this one would be 65. All right, so know how to calculate the A and the Z for different isotopes. To get A, we are adding up. Remember, it's the sum of protons and neutrons. Okay, so we define what an isotope is, and there they are. Copper. We call these isotopes by their mass numbers because their atomic number is going to be the same. So to differentiate isotopes, we have to differentiate them by their mass numbers. So it'd be copper 63 and copper 65. And these are the isotopes now. Both are copper because they have the same number of protons. Okay, but they're isotopes because they have different from each other in the number of neutrons. My computer is about to die, so let me grab my charger. Okay. So we're going to finish up really quick. Another way to represent elements, and especially now that we're getting into isotopes, defining is atomic mass. Remember, this is just the number of protons plus the number of neutrons. Atomic number was just the number of protons. All right, here's a shorthand notation at the bottom of the slide for representing the Z, the atomic number, A, the mass number, and then the symbol of the element, okay? So remember, mass number is A, atomic number was Z. You write the mass number on top, it'll be the higher number. You write the atomic number on bottom, it's usually the lower number. and then you write those just left of the symbol. Okay. So here we have an isotope of hydrogen. Hydrogen has 1 proton, but we can see how many neutrons are in this isotope of hydrogen. What do y'all think? How many neutrons? If the mass number is 3 and it represents the number of protons plus neutrons, 2. Yep, you would do 3 minus 1. There's 2 neutrons in that isotope of hydrogen. This is the kind of stuff, if I ask you about isotopes on the exam, I want you to be able to calculate Z. I want you to calculate A. I want you to be able to read shorthand notations like this. I think some of this stuff is on your chapter 2 homework, which I forget if I said or not. It is available on Mastering now, and it's due next Monday night. This was a poor example. We figured that out first lecture, so I'm going to skip it. Let's look at this one right here. Give the total number of neutrons found in this molecule. And it should say this isotope. It's not actually a molecule, it's an atom. So this is carbon. We know carbon is usually, if you look at the periodic table, its mass is usually 12. The most abundant isotope of carbon is carbon-12. But here we have carbon-14. So how many neutrons are in this isotope of carbon? So remember, to get the number of neutrons, you're going to do the mass number, and you're going to subtract off the atomic number. Okay, 8. That's what I'm getting in the chat. Yes. So you do 14 minus 6. You should get 8 neutrons. Yep. Okay. The other thing to know about isotopes is they are not equally abundant on planet Earth. We have way more carbon-12 on planet Earth than we have carbon-14. In fact, let's look at these two on this slide. We have sodium here on the left. We have nitrogen on the right. Now, for some elements, you only have one kind of atom. Okay, for sodium, it's all sodium-23. But for nitrogen, most of it, 99.6% is nitrogen-14. A very small portion, though, not even 1%, is nitrogen-15, an isotope, okay? Now, nitrogen actually is a component of the air we breathe. So pretend we're all sitting in the same room. If we're breathing in nitrogen, which we are, do you think we're breathing in A, B, or C? Which kind of molecule? Nitrogen is a diatomic molecule, meaning it's 2 atoms put together, 2 identical atoms, 2 atoms of nitrogen. Do you think that both of those atoms are N14? Do you think one is N14, one's N15? Or do you think we're breathing in molecules that are both atoms of N15? Think about their percent natural abundance. A, for sure. We're breathing in N14 because it's most of the nitrogen on our planet is N14. Now, the reason we have to think about how abundant each kind of isotope is because when we represent, if you look at the periodic table, it's too far up to scroll. I'm not going to scroll all the way back up. But if you look at the periodic table, say in your textbook or you Google one, all the masses reported for different elements have a long string of decimals. Okay, and what they've done is they have taken the atomic weight for each element on the periodic table is actually a weighted average. You guys know how to take an average. Okay, if you add up multiple numbers and then you divide by however many you added together, that's an average. So we do that, but with isotopes. So it's a weighted average of the atomic masses of each, or I should say all isotopes of that element. So if there's 3 different isotopes, we find the percent natural abundance of each isotope. We also take into account the AMUs for that isotope, the mass of it, and we multiply those together and we add them all up. And then we divide by the total number. Okay, so, all right. Well, we don't divide by the total number here because we're multiplying by the percentages. So let's look at an example with copper. All right. The type and natural occurrence of an element's isotopes determines that. Okay, that's what we just said. Let's look at an example with copper. We talked earlier about the fact that we have 2 isotopes of copper, copper-63 and copper-65. Now, copper-63 weighs close to 63. It's actually, here's the actual number in AMU, 62.9396. and copper 65 weighs 64.928. All right, so we have those numbers there. And then when we look at the percent abundance, okay, we see that copper 63 is most of the copper on our planet. Copper 65 is a little less abundant, about 30%, 31%. So what we're going to do is we are going to turn these percentages into decimals. So how do we turn a percent into a decimal? You divide by 100 and you should get 0.692. So that's 69.2 as a decimal. And then you should get 0.308. That is 30.8% as a decimal. So take the percentages as a decimal and you're going to multiply them by their mass in AMUs. And we're going to add that all up for each isotope. So the first one, we'll take the mass in AMUs of copper 63. So it's 62.9396. I want you to know how to do this for the exam. And we're going to multiply it by its percent abundance as a decimal, 0.692. And then we're also going to add it up for the other isotope, copper 65. The mass in AMU, 64.928 AMUs times its percent abundance as a decimal, 0.308. And if you add all that, if you do those multiplications and you add them up, if we had a third isotope of copper, we would put that one in the equation as well. We would just keep going for all the number of isotopes we have. Here we just have 2 isotopes of copper, so we're done after that. And when you do that, you get that the actual averaged atomic weight for copper, including all the isotopes, is 63.55 AMUs. Okay, so know how to do a problem like this for exam 1. Okay. All right. Honestly, guys, that's as far as I wanted to get in lecture for today. So I hope that didn't feel too fast because it definitely took us almost all the time last time. Maybe we had more. I think I had several more questions to answer on the front end. But that's what we're going to get to today. If you have questions, I will stick around. I know we're finishing up a little bit early, but this recording will be on Blackboard as well. So thanks for joining us today. And I will take any questions.
I have a question.
Yes, Janelle.
Do you have a time that you could meet with me on September 10th? I know you posted your office hours, but I can't remember.
So because everything's virtual this semester, I don't have like set hours that I'm gonna like sit by my computer, you know.
Okay.
But I just say if you want to meet with me, absolutely. So why don't you send me an email and give me like 2 or 3 options. Here's what I tell students: give me 2 or 3 options you're available. You know,
Okay.
Wednesday at this time, Thursday at this time, or Friday. You know, whatever. I'll tell you Wednesdays and Fridays are best for me. Sometimes Monday afternoons. Mondays
Say
will
that
be
again?
pretty. Wednesdays or Fridays.
Okay.
Mondays are also just Tuesdays, Thursdays is when we do both lectures on each day. So it's harder for me to meet with people then. But send me a couple times you're available and I'm happy to set up a Zoom meeting and work through any problems. I've actually already had some with students that have seemed to go well. And I'm happy to sit and walk through anything with you guys.
Okay. Thank you.
Yeah, you're very welcome. Any other questions? All right. Well, I'm going to hop off. Thanks for joining us, guys.